In this video, we'll complete our review of the method of partial fractions by looking at the case when the denominator has a factor which is an irreducible quadratic. We should review what that actually means. If I have a quadratic expression like ax squared plus bx plus c is equal to 0, and I try to use the quadratic formula to find its roots, in some cases, in particular when the expression under the radical is negative, I won't be able to factor using only real numbers, and I'll have an irreducible quadratic. So this will not have real roots when b squared minus 4ac is less than 0. And in that case, the expression will be irreducible, and it will contribute its own term to the partial fractions decomposition. But how that works is slightly different than what happens in the linear case. So for example, suppose I have this rational expression. In the denominator I have x plus 1, that's a linear factor. But I have x squared plus 4, which is a quadratic factor. If you tried to solve for the roots of that using the quadratic formula, you would get non-real solutions. This tells us that this factor is irreducible quadratic. The first factor, x plus 1, contributes one term, just as before. The second factor contributes another term, x squared plus 4. But what happens when the expression is an irreducible quadratic is that the numerator will now be allowed to be linear. So now I'll have an expression like b times x plus c, some linear function up top, where b and c are constants that we need to determine. But once you know that this is the right form of the decomposition, the process is exactly the same as what you did in the previous cases. So we'll begin by clearing the fractions. On the left, I'll just have the new numerator. On the right, when I multiply the first term, the linear factor will cancel, and x squared plus 4 will be the remaining factor. And in the second term, the bx plus c will get multiplied by x plus 1. The x squared plus 4 will cancel with the x squared plus 4 that you multiply by, and you'll just have that x plus 1 left. Notice the parentheses around bx plus c. Everything in that numerator gets multiplied by that x plus 1. We'll just expand out on the right side so that we'll be able to compare coefficients. I'll distribute the b's through and then distribute the c's through, and these will be the terms that I'll have: bx squared plus bx plus cx plus c. And that should be good enough to figure out what the degree 2 coefficient is, and then the degree 1, and then the constant terms of degree 0, and compare them with what's on the left side. So let's look at degree 2 first. There's an ax squared and a bx squared, so a plus b should give me 3, x squared should give me 3. For the degree 1s, it looks like there is bx plus cx, and that should give me a coefficient of 1. And then for the constant term, there's a 4a plus a c, and that should agree with the 3 over here. We now have a system of 3 equations and 3 unknowns that we have to solve. I'm arbitrarily going to make a decision here to eliminate b from the other equation. So I'm going to solve that first equation for b, and that gives me 3 minus a. And I'm going to plug that into the second equation. So b gets replaced with 3 minus a. And I'm going to record the third equation just as it was. Let's rewrite this with the constants on the right side. So the first one becomes minus a plus c is equal to minus 2 now, and then just re-recording the second equation. I see 4 times a here, and I see minus a here. So what I'll do is multiply this first equation by 4, everything by 4, including the right side, rewrite the second equation, and then I'll add them together. When I do that, the a's will be eliminated. I'll get 5 times c is equal to minus 5, so c must be minus 1. I can now substitute that into any of the earlier equations. In this case, I'll take 4a plus c is equal to 3, substitute that in, the c of minus 1, and I will get a is equal to 1. And I can substitute that into the equation here, 3 minus a for b, and that gives me b as 2. So we can go back to the partial fractions decomposition. It's 1 over x plus 1. The quadratic factor now, the quadratic term now has a b of 2 and a c of minus 1, so it'll be 2x minus 1 in its numerator. And if our goal is to integrate the expression, we now have an expression that's far more manageable. So the original integral is the integral of those terms. The first one is straightforward, it's a logarithm. The second one is a little more complicated. In fact, we can split it into two terms and make it even more accessible. It'll be 2x over that, minus 1 over the quadratic. The first term will be the natural log. To do the middle term here, I can do a substitution of x squared plus 4. The numerator will be exactly our differential. 2x dx is exactly what we have appearing here. And so we'll have natural log of x squared plus 4 after carrying out that substitution. And the final term is an arctangent form. And so you can review the formula for that. It's got a 4 there, so it'll be x over 2 and a factor of 1/2 in front of the arctangent of that. And then the constant of integration.